To CSIR JRF Net Physical Science class. Nuclear Physics class number N11. Nuclear Physics MCQ class number N11. Gellmann-Nishijima relation and other topics. Gellmann-Nishijima relation and related topics. So the first question is about Gellmann-Nishijima formula. The question is the Chamgorka is assigned a charm quantum number is equal to 1. How should the Gellmann-Nishijima formula for electrical charge be modified for 4 flavors of quarks? The charm quark is assigned a charm quantum number is equal to 1. How should the Gellmann-Nishijima formula for electric charge be modified for 4 flavors of quarks? A I3 or IZ, I3 plus 1 by 2, B minus S minus C, B I3 plus 1 by 2, charge is equal to I3 plus 1 by 2, B minus plus C, I3 plus 1 by 2, B plus S minus C, I3 plus 1 by 2, B plus S plus C. The answer is D, that is I3 plus, Q is I3 plus 1 by 2, B plus S plus C. That you remember, and there is a hint. And for that you have to remember the Gellmann-Nishijima relation. The charge Q is I3 plus 1 by 2 B plus S. For quark, it is generalized as, when we come to the topic of quark, this equation, this formula is generalized as I3 plus 1 by 2 B plus S plus C. Now comes a question based on Higgs boson. The recently discovered Higgs boson at the LHC, Large Hadron Collider, LHC experiment has a decay mode into a photon and a Z boson. If the rest mass of Higgs boson, Higgs and Z bosons are 125 GeV per c square and 90 GeV by c square respectively, and the decay Higgs particles is at rest, the energy of the photon will approximately be. That is the question. The answer is 35 root 3 GeV, 35 GeV, 30 GeV, 15 GeV. Answer is C, that is 30 GeV. This is a 2014 question. The answer is, assume H a symbol of Higgs boson, H gives Z plus Y. And energy we calculate by the energy plus Z plus gamma energy. And energy gamma energy is E H square minus E Z square by 2 EH, 125 square minus 90 square by 2 into 125. That is simplified, we get 30 GeV. You just remember the answer, 30 GeV. Now we see a question on radiative lifetime. The energies of the 3 lowest states of an atom are E0 is minus 14 eV, E1 is minus 9 eV, and E2 is minus 7 eV. The Einstein coefficients are A10 is 3 into 10 raised to 8 second raised to minus 1, A20 1.2 into 10 raised to 8 second raised to minus 1, and A21 8 into 10 raised to 7 second raised to minus 1. If a large number of atoms are in the energy E2, the mean radiative lifetime of this excited state is A 8.3 into 10 raised to minus 9 second, B 1 into 10 raised to minus 8 second, C 0.5 into 10 raised to minus 8 second, and D 1.2 into 10 raised to minus 8 second. The answer is 0.5 into 10 raised to minus 8 second. Answer is C. The rate of spontaneous decay from E2 state is given by A20 plus A21 into N1 is A2 N1, that is A2 is A20 plus A21 equal 1.2 into 10 raised to 8 plus 0.8 into 10 raised to 8 second raised to minus 1. Therefore, decay time, which is 2.0 into 10 raised to 8 second raised to minus 1, that is A2. And mean radiative lifetime is tau 2 1 by A2. 1 by 2 into 10 raised to 8, that is 0.5 into 10 raised to minus 8 second. Answer is C. Next question. A spacecraft of mass equal to m is equal to 1000 kg has a fully reflecting sail that is oriented perpendicular to the direction of the sun. The sun radiates. You read as the sun radiates. The sun radiates 10 raised to 20 watt and has a mass m is 10 raised to 30 kilogram. Mass of sun is 10 to 10 raised to 30, 10 raised to 30 kilogram. Ignoring the effect of the planets for the gravitational pull of the sun to balance the radiation pressure on the sail, the area of the sail will be, I shall read it again. A spacecraft of mass m is equal to 1000 kg has a fully reflecting sail that is oriented perpendicular to the direction of the sun. The sun radiates 10 raised to 26 watt and has a mass m is equal to 10 raised to 30 kilogram. Ignoring the effect of the planets for the gravitational pull of the sun to balance the radiative pressure on the sail, the area of the sail will be 10 raised to 2 meters square, 10 raised to 4 meters square, 10 raised to 8 meters square, 10 raised to 6 meters square. The answer is D, 10 raised to 6 meters square. You see the calculation. The sun is shown and there is a spherical surface and the sail is also shown. R is the radius of the circle, radius of the circular space from sun to the sail. The answer is D, that is 10 raised to 6. And here there is a calculation. And you just remember the answer. The calculation is mass of sail is 10 raised to 3 kilogram, mass of sun is 10 raised to 30 kilogram, and the power radiated per second 10 raised to 6 watt, joule per second, watt. Radiation pressure for fully reflecting surface. Radiation pressure for fully reflecting surface is 2I by C. But I is intensity, that is power by area. Power by area, that is P by pi r square. P by pi r, 4 pi r square. The spherical surface area, the inside area of a spherical surface is 4 pi r square, where r is radius. Therefore, radiation pressure P is equal to radiation pressure P, that is twice that of the above value, that is 2I by C. 2I by C, we put the value 5, then we get 2P by 4 pi r square C, and gravitational pull of earth is G, capital S small m by r square. Force on sail, radiation pressure to area of sail 2p by 4 pi r square c into A. P by 2 pi r square c into A, that is, P by 2 pi r square c into A is equal to Gmm by r square. A is equal to Gmm by 2 pi c by P. By P, the value is put to here. On cross multiplication, we get A is equal to Gmm, Gm into small m by 2 pi into 2 pi c by P. Put all the values and calculate. And there is no need of using calculator. We can simply calculate. Only the decimal quantity is 6.67. All of these are 2 pi and powers of 10. The answer is 6.67 into 6 pi 10 raised to into 10 raised to 4. You can approximately calculate 6.67 into 6 pi. The answer is 1.25 into 10 raised to 6. The answer D is correct. Next question. On excited state, for beryllium 8, 4b8, nucleus decays to an alpha particle which are into two alpha particles which are in a spin parity 0 plus state. If the mean lifetime of this decay is 10 raised to minus 22 seconds, the spin parity of the excited state of the nucleus is 2 plus, 3 plus, 0 minus, 4 minus. The answer is A. The parity angular momentum selection rule is alpha decay says that if the initial and final particles are the same, then I alpha must be even. If the particles are different, then I alpha must be odd. I alpha, you read as I alpha, must be odd. The ground state is 0 plus. The spin parity of excited state must be 2 plus. Thus, correct option is A. Next question. The mean lifetime of the following decays. 3 decays are given. One is P0, proton, neutral proton, or proton P0. 0 we can write like this. P, proton gives pi plus pi minus, and pi 0 meson. P is enough. P0 is not enough. P gives pi plus pi minus, and pi 0 gives gamma plus gamma, 2 gammas, and U COTS, upcork, U minus gives E minus plus gamma, not gamma, neutrino, electron anti-neutrino plus mu anti-neutrino. R topi, topi, and tomio. These are the lifetime of proton, pi meson, and mu meson respectively. They satisfy the condition. The lifetime of these particles, proton, pi meson, and mu meson satisfies condition. Topi less than tommu, tommu less than topi less than topi, topi less than topi less than tommu, topi less than tommu less than topi. The answer is C, that is topi less than tommu, pi less than tommu. That depends in terms of the mass. Proton has greater mass, and in this group, mu has the lowest mass. So the lifetime depends upon the mass of particles. and solution is given here. The characteristic time for strong electromagnetic and weak interactions are 10 raised to minus 23 second, 10 raised to minus 21 second, and 10 raised to minus 11 second. P gives pi minus plus pi plus pi minus. It's a strong interaction. Therefore, tau P is equal to 10 raised to minus 23 second. Pi 0 gives gamma plus gamma is electromagnetic interaction with the lifetime, decay time, gamma P is equal to 10 raised to minus 21 second. And mu minus gives E minus plus nu mu. It's a weak interaction with the tau is equal to 10 raised to minus 11 second. So 10 raised to minus 11 is the largest and the smallest is 10 raised to minus 31. So we can write tau P less than tau pi less than tau mu. The correct option is C. That is all with your 11th class on nuclear physics. We continue the class. Thank you.